Hello friends, this is Ayush Sharma and today we are going to learn about MOSFETs. In this video, I will try to quickly brief you about MOSFET basics and then we will switch to MOSFET applications. After seeing this video, you will be able to use MOSFETs in your power electronic circuits for your hobby and professional projects. So let us begin. As we all know that MOSFET stands for metal oxide semiconductor field effect transistor, and this transistor is operated by providing a voltage signal to its gate. So here we have a real image of MOSFET. If you ignore the colors, it is basically the real image of a MOSFET. So in case of a real MOSFET, these leads are metallic and this body is also metallic. Okay, so it has the first terminal gate, second is drain, and third is source. And you can see the drain color, we have provided it as green and its body is also green. Sorry, the body metallic part is green. So it means that body is at drain potential and it is internally connected. So in case if you are using MOSFETs in parallel and you want to parallel them on a heatsink, you can simply place these MOSFETs on heatsink and tie them on heatsink, and you need not to connect their drain terminals together. This side on PCB you only have to make path for the source terminal. Okay, so let us move to the classification of MOSFETs. Here you can see in this image we have provided the classification. So MOSFET is basically of two types. One is enhancement, another is depletion. Again, in both the types we have P channel and N channel. You can see here also it is P channel and N channel. So the enhancement mode type of MOSFET is that MOSFET in which channel is not present. You have to induce this channel by providing external gate signal. But in case of depletion mode MOSFET, channel is already present. You have to remove this channel sometimes to turn the MOSFETs off. Okay, and again here we have the types N and P channel. So a P channel MOSFET means the substrate material of the MOSFET is of N type and its channel is of P type. Similarly, a N channel MOSFET tells that its body is of P type and its channel is of N type. Okay, now let us see the symbols. Here we have the four symbols. You can notice these lines are the dotted lines. The dotted lines means it is a enhancement mode because channel is not present, and here the line is continuous. It means channel is present, and that's why it is depletion type MOSFET. So out of four you can now easily identify this one and this one is the enhancement mode, and this one and this one are the depletion mode MOSFET where channel is already present, and in this two channel is absent. Now there is another difference. You can see here arrow is going inside, here also it is going inside, here it is going out, and here also it is going out. So in case of N channel, arrow is going inside in both the cases, and in P channel arrow is going outside in both the cases. You can remember this by simply a basic technique that a positive thing always gives something out of it. So both these transistors are giving this arrow out of it, and just opposite to it, a negative thing will always take everything inside it. So you can see in both the images arrow is going inside. So now you can easily tell that this is a depletion kind of MOSFET and arrow is going out. It means positive. So it is P channel enhancement MOSFET. And if I will ask you this, then you can say this line is continuous, then it means it is a depletion kind of MOSFET, and arrow is going inside, it is taking everything in, so negativity, that means it is n channel depletion MOSFET. So you just remember, I have given this remembering technique just to remember the symbols. This has no relation with the exact theory. Let's move on to the structure of MOSFET. But before moving to the structure of MOSFET, I want to tell you a very important thing about MOSFETs in power electronics. You will mainly see only n-channel enhancement mode MOSFETs in power electronics. These MOSFETs you will never see in power electronic circuits, and p-channel MOSFET, p-channel enhancement MOSFET has very less application compared to n-channel enhancement type MOSFET. Now there is question, why? The answer is, in case if you are using these depletion kind of MOSFET, then you are already in conduction state and you have to provide some gate signal to turn it off, and this is not the desirable condition in power electronics for safe applications. Now let's move to enhancement type. Enhancement type are the good ones, and here we have to provide some signal to turn them on. Now a n-channel enhancement type MOSFET will require a positive gate signal to turn on, and a p-channel enhancement type MOSFET will require a negative gate signal to turn on. So now you can think, to provide a positive gate signal to turn a n-channel MOSFET is easy, because if you are using a microcontroller, you can provide this. If you are making any electronic driver circuit, you can also easily provide a positive supply, but negative supplies are not much popular. So if you want to provide a negative supply from a microcontroller to this p-channel MOSFET to turn on, then you have to add some additional circuits. So this is one reason why we avoid p-channel MOSFETs. Now the another and major reason why we use n-channel MOSFET in power electronics more than a p-channel is that in n-channel you can construct a high capacity MOSFET in smaller area compared to p-channel. This is because of the mobility of electrons. In n-channel, channel is of n-type material and it has nearly twice mobility compared to holes. But in case of p-channel, the channel is of p-type material and holes have half mobility. So you can pass twice current in same area with n-channel MOSFET, but with the p-channel MOSFET you will roughly be able to supply only half of the current of n-channel MOSFET. So we always try to use n-channel MOSFET in power electronics. Also, the drain to source resistance, the resistance between this and this terminal is less in case of n-channel MOSFET, and because of this there will be less conduction losses. We know that we can calculate the power loss by formula I square R. So if we know what is the amount of current which is flowing through this, and RDS on, that is the drain to source resistance, which we can get from the data sheet. So simply by making I square R we will get the losses. So in case of n channel, these losses will be less compared to that of a p channel MOSFET of same capacity. Now let's move to the construction of MOSFET. So this is n channel enhancement MOSFET, and here we have n material here and here near drain and at source, and this complete area is covered with p-type substrate. So in this case you can't see any conducting channel between the source and drain, there is nothing. So if you want to start conduction, we have to create a channel in between this, and to create that channel we have to provide gate of positive potential, which should be higher than the threshold voltage of that particular MOSFET. Okay, and at that time we also have to connect drain and source to the power supply voltage. Okay, so now you can see in the next diagram, when we have provided gate to source voltage of threshold voltage which is higher than the rated threshold of that particular MOSFET, a channel is induced. Now when you will provide drain to source supply, conduction will take place, current will flow through this kind of MOSFET. Now you can see this graph. In this graph we have explained that after increasing the gate to source voltage slowly from 0 to 5, the drain current increases. So at 1 volt drain current is near this, and at 5 volt drain current is here. So it is increasing with the increase in gate to source voltage in case of n channel MOSFET. Here we have a small example of a circuit. Here we have connected a battery to the drain, but in series we have resistor and diode, and at source we have connected with the negative terminal. And here you can see we are going to provide positive supply to this MOSFET when this switch is going to pushed to on. Okay, otherwise this gate terminal is always connected to negative side. It means it will be at zero potential. So once we on the switch, this MOSFET will turn on and this LED will light up. Now this is about the construction of P-channel MOSFET. These MOSFETs are not much used in power electronics, but we should know about this as it also has some applications. So this is the N-channel substrate, and this is the N-type substrate, and here we have the P-type material at this side and P-type material at this side. So both at the drain and source we have the P-type material and channel is not present. So in this type of MOSFET, which is a P-type MOSFET, when you will provide a positive signal like a N-type MOSFET, this will not turn on. Here you have to provide a negative gate signal to turn it on. So here you can see we have started providing negative signals, and when we are increasing this negative voltages, current is increasing here. Okay, so after providing appropriate gate to source negative voltage, which should be above the rating of threshold, gate to source voltage, it is negative, so above means more negative, then this device will turn on, and first the channel will be induced and then it will turn on. And for conduction you have to connect the drain and source terminal to the voltage source. So by this table we can be able to understand what type of gate polarity we need to provide to a particular MOSFET to keep it on or to keep it off. So here we have the positive gate, here we have the zero potential gate, and here we have the negative gate, and here we have the different types of MOSFETs, and their symbols are given in front of their name. Okay, so for example, let us consider this one. This is the N-channel enhancement MOSFET. So to keep it on, you have to provide a positive gate to source voltage, then only it will be on. Otherwise, in both the cases, when VGS is 0 or VGS is negative, it is off. Now take another example from depletion kind of MOSFET. So let us take this example. In case of P channel depletion MOSFET, it is off when VGS is positive, but it is on when VGS is at 0 volt or when VGS is at negative voltage. So it will always in on condition when you have 0 voltage or negative voltage. So to keep it off, you have to provide a positive gate voltage. Okay, now let's move on to understand MOSFET datasheet. So every MOSFET manufacturers, they provide absolute maximum rating for each MOSFET, and this is the screenshot of a datasheet of N-channel enhancement mode MOSFET, and these are the maximum limit. Out of these, the important ones are these: drain to source voltage, it is 60 volt; gate to source voltage, it is plus minus 20 volt; and continuous drain current, it is 50 ampere at 25 degrees centigrade; and continuous drain current at 100 degrees centigrade is only 36 ampere, and its Tj is, that is the junction temperature, is limited between minus 55 to 175 degree centigrade. So in any circumstances you should not go beyond these limits. If you will exceed these limits, your MOSFET will fail. So first thing, drain to source voltage. For design consideration, you always have to take some margin over here. So if you are going to work on 60 volt, then this is not the right choice. So in place of 60, you should directly apply a thumb rule that you should reduce it by 20 to 25%. So if you are using this MOSFET at drain to source voltage 40 volt, then it is okay to use it, but don't ever use it for 60 volt or 58 volt, something like that. Now this is the gate to source voltage, then this is the voltage which you have to provide at gate to turn this N channel MOSFET on. Okay, so here you can see that you cannot provide anything which is above 20 volt. So for safety margin, again you should take around 10 to 20% lower gate to source voltage. And one more thing, when you will see the curves in this data sheet, you will be able to see a curve. That curve will represent one side drain current, okay, and this side you will have the different gate to source voltages. On particular gate to source voltage, here you will be able to get a particular current capacity of that MOSFET. So by that also you can be able to finalize the VGS. Okay, now this is the current rating. So this MOSFET can handle up to 50 ampere of current when its case temperature Tc is at 25 degrees centigrade. So you have to maintain this. If MOSFET is started heating up, then you have to provide cooling to maintain it at 25 degrees centigrade. Otherwise you will not be able to use it at 50 degree. You will not be able to use it at 50 ampere. Okay, but here also you should take the margin. Normally these MOSFETs are not used at this ampere rating because it is very difficult to cool them. You have to provide heat sink, you have to provide forced air cooling, sometimes you need to provide water cooling if you want to go to reach this level at this ampere, and this is highly impossible kind of thing, but these are the maximum ratings. And the next thing is, at when the case temperature is 100 degrees centigrade, you can go only up to 36 ampere, but we always take some margin in these currents. Okay, I will later on make another video on calculating the junction temperature of a MOSFET and at what current you will be able to use them. Now here we can see the operating and storage temperature range, operating junction and storage temperature range. So it is in between minus 55 to 175. So you should always use this MOSFET in between these range. And one thing that you need to notice is that if you have measured its case temperature, which can be at say 140 degrees centigrade, then there are chances that its junction temperature could have reached 175 degrees centigrade, because junction temperature will always have higher temperature compared to its case. Okay, now let us move to other parameters. So here we have some other parameters, and let us know about these. In this we have the two important parameters. One is gate to source threshold voltage. Okay, so it has gate to source threshold voltage minimum 2 volt and maximum 4 volt. So if we want to turn this MOSFET on, we should provide minimum 2 volt to 4 volt. To ensure a turn on, we should always select this value. It may happen if you have selected 3 volt and MOSFET is not turning on, so for that case you have to consider this, but that particular MOSFET may turn on at 2 volt, but this is not guaranteed. So you should provide this 4 volt VGS to turn this MOSFET on, and above 4 volt you can go up to 20 volt, which we have seen in the previous, this one. VGS plus minus 20 volt is the maximum limit. We should never cross this limit. Now you can see here we have drain to source on state resistance. This is 0.028 ohm. So in case of MOSFET, if this resistance is less, it is good, because less resistance means it will heat up less losses and less heat up. Okay, we will use these things in calculation of power loss. Now let us come to its application. So here we have two types of MOSFET. One is N channel here and another is P channel here. So here we have these two circuits, which are basically MOSFETs in switch configuration. So these MOSFETs are acting as a switch, and to use them as a switch, what you have to do. Now let us consider the case of an N channel MOSFET. In case of an N channel MOSFET, you have to provide positive to its drain. Here we have a load connector in series, so positive is connected to drain through a lamp, and ground is connected to source. This we need to remember, that positive should always be connected to drain and ground to the source. And as it is a N channel MOSFET, then it requires a positive voltage to turn on. So from gate we have to provide a positive voltage to turn it on. Now let us take the example of a P channel MOSFET. In case of a P channel MOSFET, here we have the circuit diagram, and in this time source is connected to positive. This time drain was connected to positive, but at this time source is connected to positive and drain is connected to ground potential through a load. Okay, in both the cases you can see load is connected in series with the drain. Here also it is connected in series with the drain, and here also it is connected in series with the drain. Next thing to notice here is that this time you have to provide a negative gate signal to turn this MOSFET on, because it is P channel MOSFET. Okay, now let us concentrate on this and this resistance. Okay, here also we have this Rin and RGS. So in case of N channel MOSFET, this Rin resistance is normally, you can have it at 20 ohms, 33 ohms or 1 kilo ohms also. And this RGS resistor, this one is typically at 10 kilo ohm. So the application of this RGS resistor is that in case you have not provided any gate signal over here and you have just touched this terminal by your finger, then this MOSFET may get turned on if you have not this resistor over here. Okay, also when you will provide a positive signal to this gate, and you have this resistor not connected over here, then because of some charges it will not immediately turn off. So for that reason also we have to connect a RGS resistor here, so it will protect MOSFET from false triggering, and it will immediately switch off the MOSFET when gate pulse is removed. But in case of P channel MOSFET, we have different polarity connection to this resistor. Here both the resistors are doing nearly same job, but here you can see the gate resistor is tied to the VDD, that is the positive side, but here the gate resistor was tied to the ground side. So what happens in this case, when you will provide a negative signal, this MOSFET will turn on, and this resistor will provide a positive potential here. So when this negative signal is not there, immediately this positive signal become more prominent and this MOSFET will immediately get turned off. And if you will not provide this resistor, then this MOSFET may get turned off or may not get turned off. We can't guarantee because it has some charges, and this may also get false triggered. So to prevent that also you can provide this resistor. Now let us move to a complementary MOSFET motor controller. Here we have used two different MOSFET. One is the P channel enhancement MOSFET and another is the N channel enhancement MOSFET. We have tied their gates together and they are connected to a motor load. What we have did here is that we have provided positive to the P channel MOSFET and we have provided negative to the N channel MOSFET, and from here we are providing positive or negative pulses. So when we will provide a positive pulse, then only this N channel MOSFET will turn on and current will flow from this ground to negative potential, and motor direction will be like this. And when we will provide a negative gate pulse, then this will not turn on, only this MOSFET will turn on, and that time current will flow from this direction to this direction, from positive to ground, and motor will have a reverse direction. Now let us talk about the MOSFET losses. A MOSFET has majorly three types of loss. The first one is conduction loss, second one is switching loss, and third one is the reverse loss of the diode which is inside a MOSFET. So this conduction loss is the most prominent. I have shown a screenshot of conduction loss of a particular MOSFET which I have calculated. Here you can see this, the conduction loss is 1.2 watt, switching loss is just 0.18 watt, and reverse recovery loss, which was the loss of diode, is just 0.19 watt. So if you want, you can ignore these two losses and you can consider this only for your hobby projects, and in your professional you can consider this also. Or what you can do is that you can take this and you can take some margin for these losses. So now here we are going to calculate the conduction losses. Now to calculate the conduction loss, we need to know the current which is flowing through this path. So we can know this current by using multimeter or by using Ohm's law. So once we have the current, we have to make it square into RDS on. So RDS on is 0.028 ohms into duty cycle. If duty cycle is 50%, we can put 0.5 over here. If it is 40%, then we can put 0.4 over here. If it is a continuous DC, then we will put 1 over here. So here we have solved it, and after solving this we have got 0.056 watt. So this is a very small loss, and this loss is calculated for 2 ampere current. So for 2 ampere current, this will only have this much of loss, and this will depend on this resistance. If this resistance is high, it will have high losses. And yeah, this we have calculated for 50% duty cycle. That's why here we have multiplied it with 0.5. Now this is the switching loss. To calculate switching loss, this is the formula, and here we have calculated the switching loss. And to calculate switching loss, we have to consider these two parameters from datasheet. This is the rise time and this is the fall time. We have to make addition of both these. Here we have added this 2. Here it is the applied voltage. This is the current flowing through it, divided by 2 into addition of rise time and fall time, multiplied by switching frequency. This is the frequency of this pulse, and here we have got the losses. This is also very less. It is 0.009696 watt, so we can ignore this for this case. And now we have diode switching loss. Okay, so to calculate diode switching loss, you can see here this is a diode inside the MOSFET in reverse direction. You can see this diode symbol in data sheets available with the MOSFET manufacturers. Okay, so here we have to consider diode reverse recovery charge. This is QRR, and here we have to take its maximum value for calculation, because always we have to consider the worst condition. So 0.80 nanocoulomb, so 0.80 into 10⁻⁻5 into applied voltage into switching frequency of this pulse. So this has given us this, and finally we have 0.000384 watt loss. So this is also very less. As I have already told you that I will make a separate video for calculating the temperature of MOSFET, that is basically thermal management. But here, as we have already calculated the losses, so I will tell you what will be the temperature of this particular MOSFET if we are not going to use any heat sink with it. So to know that, we have to take this thing. This is maximum junction to ambient temperature. This is junction RTH, junction to ambient, and it is maximum 62 degrees C per watt. Okay, and when we will add our losses, then we will come to 0.066, which was our summation of conduction losses plus switching losses plus reverse recovery loss of diode. So what we have to do here is that we have to multiply 62 to our total losses. So our total losses is 0.066 into 62, and this gives us 4.09. It means when we are not using any heat sink, the temperature of our device will be at 4.09 degrees centigrade above ambient. So if the ambient temperature is 30 degree, then our MOSFET temperature will be 34.09 degree centigrade. Thank you and have a nice day. Keep watching my videos, and if you have liked this video, please click on like button and share this video with your friends, and don't forget to subscribe me.